We now have a small change in name. It's Edoardo Vittori, Associate Professor from SDA Bocconi. Can you hear us?
Hello, yes, I can hear you. Can you hear me?
Welcome.
Hello, thank you for having me.
And you can go straight into your talk. Thank you.
Okay, perfect. So today I will be talking about in-orbit refueling, the technical and economic feasibility of moon mine propellants, specifically looking at the transportation, storage, and distribution systems. So this is an ongoing research work between two teams from two different universities. The Space Economy and Evolution Lab from the Bocconi University and the Sapienza University of Rome. I have been collaborating with the SE Lab for several years now, and my background is in mathematics, finance, and artificial intelligence. But today I will be speaking on behalf of both groups. So next slide, please. Okay, so no, I think it went one too many. So, I still see the wrong slide. In any case, briefly, what I will be talking about today is the current state of works regarding this project we've been doing. And the main objective of this project is to answer the question whether it makes sense from both a technical and business perspective for a private company to enter the space of in-orbit refueling. And I will start by explaining the technical assumptions we have made and how I'll go in depth on some of the aspects we have decided to consider, and then go on to explain the next steps we intend to take, and specifically how we intend to tackle the economic feasibility. So in-orbit refueling, why is it interesting? Well, we all know that, for example, if there is a satellite which is running out of fuel but still perfectly functioning, it is possible to extend its lifetime if there was a possibility of refueling it. Other possible benefits of in-orbit refueling are the reduction of mission failure or the possibility of increasing payload capacity for launch vehicles, giving certainly more mission flexibility. So from our studies, there will be a large number of companies looking to develop in the cislunar space and beyond, which will be potentially interested with in-orbit refueling. And one of the things that in our analysis is extremely important is the fact that this fuel can be taken from the moon. Now, the fact of taking fuel from the moon is interesting because it requires a lower amount of energy. A lower amount of energy means also, from an economics perspective, a lower cost. When I talk about fuel from the moon, I am referring to the fact that we can extract the ice at the lunar poles and use that in order to create liquid oxygen and liquid hydrogen, which can be used with the compatible systems. Now, one of the difficulties is, in general, when we need to store propellant in space, is the fact that it needs to be kept in cryogenic conditions. But we will see more about this in the next slides. So we have decided to analyze two main architectures, a heavy lift launcher architecture and an orbiting depot architecture. In the heavy lift launcher case, just to give a basic example of how it should work, you can think of two launchers launching at a short distance of time for a single mission. One launcher has the payload, and the other launcher has the extra fuel. Once in orbit, they need to rendezvous. There has to be an automatic docking, and then the fuel will be transferred from the launcher with the extra fuel to the payload. In the orbiting depot case, instead, you can think of having essentially gas stations which are orbiting in the just lunar space. And in this case, a launch from Earth could dock to one of these orbiting depots, refuel, and then continue on its mission. Well, the main difference between these two architectures is that in the heavy lift launcher case, it is potentially doable starting today, while in the orbiting depot architecture, we still need to build the entire framework. But the positive point about the orbiting depot case is that it is compatible with fuel taken from the moon. Okay. Next slide, please. I don't see the next slide, but okay. So the next slide is on the technical requirements necessary for in-space propellant storage. And the question here we decided to look at what can potentially be used. So one of the main conditions is that these fluids, the liquid hydrogen and liquid oxygen, need to be kept at really low temperatures. In space, obviously there's solar radiation and also radiation which can be coming from Earth. And so it is possible to use, for example, sun shields in order to protect the fuel from this radiation. There will also be heat coming from the electronics, and so we could perhaps use advanced materials that limit this heat transfer. Other problems that may come from the use of such liquefied gases are the fact that they tend to boil off. But there are technologies such as pressurized tanks or venting and vapor cooling systems, or even these vapored gases can be used for station keeping. But so how can we design this system? So the simple design is just two tanks, one for the liquid hydrogen and one for the liquid oxygen, which can be stuck together. Perhaps to keep a low weight and a smaller design, it is possible to utilize a common bulkhead for both tanks. And then in these tanks, we'll need to also have advanced fluids management and fluids transfer systems. But there are existing technologies, such as the one that you can see in the slide. And finally, one last thing to note is that it will be necessary to consider carefully which will be the design, the requirements for the mission. In fact, if the fuel needs to be stored in space for a longer amount of time, it will be necessary to add additional insulation, and so the space remaining for the fuel itself becomes less. So now, next slide on the depot-centric architecture. I'm not seeing any slides right now, but I can just talk about it. Anyway, the depot-centric architecture, as I was mentioning, can be just a basic concept, essentially with two tanks plus the avionics, or we can upgrade it in order to make it more interesting for potential clients. For example, if there is a manned mission which wants to land on the moon, it can leave Earth without without an aerobraking system, for example, and dock onto the depot. While it's refueling, it can mount the aerobraking system and then continue its mission towards the moon. Similarly, it can also be possible to mount a crew transfer vehicle, a reusable upper stage, or any other type of additional material. Okay, so now the slide on the orbital placement. Here I'd like to discuss two optimal placements we have analyzed. And they have different characteristics, both from the point of view of the technical requirements and then the economic and financial results. Specifically, if we have considered an orbit, the LEO orbit and the L1 orbit. So in LEO, from the technical point of view, it will be more complex to handle the fluid management and the thermal insulation. This is because you're constantly passing between light and darkness, and also there is the gravitational pull of the Earth, characteristics which are easier to handle in L1. On the other hand, it is easier to arrive in LEO because it's an orbit, while for L1 you need to wait for the appropriate window. Instead, from a market point of view, we imagine having clearly different customers. In LEO, we expect the interest of satellites or just lunar missions to the moon or to GEO. While in L1, we expect the interest of missions, such as missions going to Mars or other interplanetary missions. And here in the slide, you can see an estimate which has been taken from a work of Sowers, which estimates 210 metric tons of propellant in LEO and 280 metric tons of propellant every 2 years in L1. Sowers also does an initial pricing. I do not want to delve too much into this. I just want to mention that a pricing of the fuel from the Earth or from the moon. The main thing to keep in mind is that in order to have economic sense to take fuel from the moon, we need to make sure that the fuel coming from there is cheaper than that coming from Earth. Okay, now the slide on lunar supply. Here, I'd like to just give an overview of how the entire system could work. So we have a company, let's say Lunar Outpost Inc. Incorporated, which is handling what is going on the moon. So he is in charge of extracting the ice and transforming it into liquid hydrogen and liquid oxygen, storing it on the moon. At this point, this fuel needs to be transported to either the depot in L1 or the depot in LEO. This can be handled by another company, which uses, for example, the Moon Shuttle to go to L1 and space tugs to go to LEO. Finally, a third company, or the same company as the transporter company, can be in charge of keeping the orbiting depot, which, for example, can be an advanced Centaur in a simple case, or can be something more complex, similar to a space station, as we saw previously. Okay, so now I'd like to comment on the roadmap we intend to take in order to analyze the economic sustainability. And here we will tackle it both from a strategic and a financial perspective. In the strategic case, we will start by analyzing the internal and then the external environment. So for internal environment, I am talking about characteristics internally to the potential project or company. So the initial investment costs and the costs of operating then the entire project throughout. These two quantities will be deriving from the technical assumptions which the Sapienza University is working on. Then we will go on and work on the external environment. So go back and think about exactly which are the potential customers in LEO and which are the customers interested in L1 and estimate the demand, not just the current demand, but also the future demand. At this point, we will also reason on the competition arena. So if there is going to be one transport and distribution company, if there's going to be multiple, if there's going to be one which takes fuel from the moon, another one which takes fuel from the earth, and all the possible scenarios. At this point, we can go on to the financial analysis, where we start by analyzing all of the potential risks, which are not just technological risks, but also more generic risks like I don't know, geopolitical risks or any other type of risk that can influence the cash flows of our project. So at this point, we can go and estimate the cash flow. So how much fuel we intend to sell, and so how much revenue we will have. What will be the ongoing costs of the project? What will be the capital expenditures? And once we have found all our cash flows, we need to understand exactly how the optimal capital structure of this new business will be. So what is the optimal equity structure and optimal equity and optimal debt structure? Because from this, we will understand how much investors will want in return in order to invest in this project, and how much a bank might ask to give some debt in order to finance this project. Being such a risky project, we expect the cost of capital to be extremely high. And so one of the main assumptions we intend to make is the possibility of entering a public-private partnership, thus having financing coming from some government or governmental entity, which will help to lower the risk and thus encourage investors to also enter the financing of the project. So once we have all this information, we can finally evaluate our company with the net present value, which will hopefully be positive. So at this point, in order to stress all assumptions, we will do a sensitivity and Monte Carlo simulation. So now for the concluding slide. So today we learned about this new project which we are currently working on. So we want to answer the question whether it makes sense from both a technical and economic perspective for a private company to enter the Inorbit refueling business, a private company which would concentrate on the transportation, storage, and distribution parts. So we've seen the technical assumptions that we will be taking and the roadmap for the economic sustainability analysis. So at this point, if you have any suggestions or any questions, if there is some time now, or feel free to contact me by email, or if there's something very technical, you can write to Michele Pasquali from Sapienza University. Thank you for your attention.
Thank you so much, Eduardo. There are a few questions coming in online. Trying to keep the time here, but I'm going to throw to Mel to ask you at least one question. Mel, over to you.
Yes, thank you, Lisa. Many questions have come up, but I will just pick up the one from Giovanni and is linked to one from Gordon, which is the base of the cost estimates for the propellant of the moon, and especially if you have considered the SpaceX Starship refueling strategy in Earth orbit.
Okay, yes. So as I mentioned, this is an ongoing project. So regarding the cost estimates of the fuel from the moon, we are starting with the costs which I showed previously in the slides. Now, I know there were, at least I saw some problems with the slides, so I'm not sure if you guys got to see it. But starting from a work that Sowers did, he estimates the cost of propellant on the moon, which is $500. And starting from that, we intend to use the same assumptions to build then the pricing on the other orbits. And now Starship is certainly something which we need to understand how to insert in the whole analysis. Obviously, it is something that is currently under construction, so it's hard to understand and to know exactly how it will work and how much fuel it will require, but we will be keeping up to date with the new developments and hopefully also insert it into our study.
Thank you very much, Eduardo. Please.
Thank you so much, both of you, indeed. And we've had another couple of questions coming in, which we did yesterday, also asking if all of the presentations, including yours, Eduardo, can be offered to be collated by the end of the week, to which the whole team here have said yes. So by the end of the week, all of you will be able to see all of the speakers' presentations online or in some format they will get to you.